class. So today we are going to look at what is known as Lebesgue outer measure, its properties. Although I have written it as a construction of Lebesgue measure, I will not say what is Lebesgue measure unless and until we do many things. So let's formally define. In the last class we saw how to define blah blah blah, but anyhow, let me begin with the definition. First one. So as usual, so whatever we did, I'm just writing it for any E subset of R. The Lebesgue outer measure of E denoted M star E is defined as M star of E equal to infimum over infimum of all sum of the lengths of the intervals such that the union they cover, and not only that they cover E, and each IN is an open interval. For each NN. Yes. Fine. So this is the what is known as the Lebesgue outer measure. Yes. So it was originally, this definition is due to Lebesgue, and therefore it is called as Lebesgue outer measure. Why is it called as outer measure? All these things, when we do abstract outer measures, then you'll understand. When we do some abstract concepts, there we will understand. Right. Okay, so here are some simple observations. First one. Yes, what is M star of an empty set?
Zero.
Zero. Right.
Zero, sir.
Right. 0. Yes, fine. Why is it 0?
Because empty set is contained in 0 to epsilon, and we can decrease the epsilon as much as we want.
That's it then. Right. So you choose I1 as the interval 0 to epsilon, open interval 0 to epsilon, and then choose the remaining to be empty. That's it. And that should help you. Yes. This is first thing. Second thing. If E contained in F, then, well, what can you say about M star of E and M star of F? Which one is bigger? Which one is bigger?
M star F is bigger.
M star F is bigger.
F is bigger. Why?
It may be possible that there is a smaller collection of intervals which contain E but not F.
Maybe.
Sir, strictly, I mean, E is if E is a proper set, then there exists. But if E is equals to F, then we cannot.
E is contained in F. So what can you say about See, simple observation is that one thing that you can observe is that any open cover of F is also an open cover for E. And therefore, the collection of open covers for E, it's a larger collection, naturally. Right? And that will tell you that M star E is less than star F. Right. Fine. So, well, I'm putting it as a lemma next one, but again, you can easily observe that Lebesgue measure of a countable set is, sorry, Lebesgue outer measure. That's the right one. Actually, I should have said outer measure of a countable set is 0. Yes, how do you show this?
Each point is contained in some each point A can be contained in some A minus epsilon, A plus epsilon, and then we take A minus epsilon by 2, A plus epsilon by 2, then by geometric
That's it
series
done.
we
Right.
get.
Right. So let E be a countable set So let me list down the elements. Let E equal to x1, x2 up to whatever it may be. So because it is countable, so be an enumeration. Of the set E. Yeah, so this is one of the common tricks or thing that we are going to do again and again. Let epsilon greater than 0. Now, for each k in n, let ik be the open interval. Of course, our interest is only on open interval. Xk minus epsilon upon 2 raised to the power k plus 1 to xk plus epsilon upon 2 raised to the power k plus 1. Right? Yeah. So now, once you have chosen this, now it can be easily observed. Note that E is contained in union over k in n ik. Yeah, this you can easily observe because xk is contained in the interval ik for each k, and therefore E is contained in this union. Fine. Therefore, 0. Yeah, so this m star of any set, it's always a positive quantity that you can easily notice. M star E, which is less than or equal to, it is by definition, it is the infimum, and therefore, if I add the lengths of each of these individual intervals, it is going to be naturally bigger than E. Length of ik. But then these lengths of IKs, how did we define? So, well, this is nothing but lengths of ik, it is epsilon upon 2 raised to the power k. So now you can notice that this is going to be just epsilon. Fine. So since epsilon greater than 0 is arbitrary, it follows that m star of E is equal to 0. Fine. So yeah, so this is one of the common tricks that we are going to use again and again in many places. This epsilon trick. Yes. Now comes a corollary. So having said for countable set, singletons have Lebesgue outer measure 0. Yes. Yeah. So choose E to be x, then you should be able to get it. Proof. Or, well, whatever you want to do. It's all up to you. Yes. So next one. So what is the point for introducing this concept? Why did we introduce this concept? This m star E. Why did we introduce? Why did we introduce this m star E?
To overcome the drawbacks of Riemann
We
integration.
wanted to generalize the notion of length, and therefore we introduced a new concept. Fine. But when you want to generalize the concept of length, what is that we wanted? We wanted something which makes sense for all subsets. Fine. But on the interval, what is that is expected? What do you expect on the interval?
The
Sir,
length
the
of
measure.
interval.
So on the interval, it should be the length of the interval. Right. Yes. So that's what we are going to do now. So Lebesgue outer measure of an interval is equal to its length. Right. Proof. So let I be an interval. Right. Yeah. So case 1. I is closed and bounded. Say I equal to AB. Right. So we are going to show that m star of I is equal to B minus A for this closed and bounded. As usual, let's start with an epsilon positive. Let epsilon greater than 0. And then, so once you have chosen an epsilon, let me choose an interval I epsilon as a minus epsilon, comma b plus epsilon. Yeah, maybe you can choose it as by 2, doesn't matter. So since I epsilon is an open interval, and I is also contained in I epsilon, which means I have an open cover. And therefore, it follows from the definition. Definition of Lebesgue outer measure. That, well, m star of I is less than or equal to length of the interval I epsilon, but length of the interval I epsilon is b minus a plus 2 epsilon. Now, this is true for every epsilon positive, as this is true for every epsilon greater than 0. It follows that m star of I is less than or equal to b minus a. Right. So now we will have to show that m star of I is greater than or equal to a. Right. Fine. Well, so we now prove the other way inequality, that is m star of I is bigger than or equal to b minus a. Right. Fine. So now note that this is equivalent to proving this is equivalent to showing that summation over k in n, length of ik is bigger than or equal to b minus a for any countable collection ik of open intervals covering I. Right. Now what is I? What is I?
Closed interval AB.
Closed interval AB, therefore it is
Compact.
compact. Right. So by Heine-Borel theorem, I is compact. So since I is, it is not just closed, it is also bounded, in fact. Closed and bounded. By Heine-Borel theorem, I is compact, and hence this Ik has a subcover, has a subcollection, in fact a finite subcollection. Collection covering I. So without loss of generality, let us assume that I1, I2, In is that subcollection. Covering I. Right. Fine. Right. Now let now, so therefore, so once having said therefore, what does it tell us? So I is contained in union. I'll write it as k running from 1 to n Ik. Fine. That is the interval a comma b is contained in union k running from 1 to n Ik. Fine. Now since so once you know that the interval AB is contained in this, that implies that A belongs to this. So since A belongs to this union, there exists K1 in 1, 2 up to N such that A belongs to Ik1. You get at least 1 with this property. Right. So now let me call Ik1 as A1 comma B1. Right. So now as A belongs to this open interval A1 B1, A1 strictly less than A, strictly less than B1. So if B less than or equal to, no sorry, if B less than B1, then we are done. What is that done? Right. So if B belongs to B1, then we are done. Okay, fine. Otherwise, if not, there exists K2 in 1, 2 up to N, but minus with K1 such that B1 belongs to Ik2. So let me call the interval Ik2 as A2 comma B2. Right. Now since B1 belongs to this interval A2 B2, A2 less than B1 less than B2, right? So if B is less than or equal to B2. Sorry, less than B2. Then we are done. Why? Well, now, at least now let me write. Summation k running from 1 to infinity, length of ik. Yeah. So this is going to be bigger than or equal to B1 minus A1 plus B2 minus A2, which is equal to B2 minus A2 minus B1 minus A1, right? Yeah. Yes, so this is exactly what we want. And now look at the, yeah, so B2 minus A1, sorry, A2 minus B1, yeah, this is a negative quantity, A2 minus B1, and therefore, yeah, so B2, so well, let me write a different way, which is going to be same as B2 minus, well, rather than writing it here, let me write it here, which is same as B2 minus A1 minus A2 minus B1. Now A2 minus B1, it's a negative quantity, therefore I am adding a positive quantity on the whole. Therefore, this whole thing is bigger than B2 minus A1, because I have added something. And now B2 minus A1, this whole thing is bigger than B minus A, and this is what we wanted. Right. So if B1 belongs to, sorry, if B less than B1, then we are done. If B less than B2, then again we are done. But how long are we going to proceed?
So since the collection of intervals is finite, we can exhaust it.
Exactly right. So we continue this process. Until it terminates. In fact, so it must terminate as there are only finite number of intervals. Right. Thus, we obtain a subcollection IKI, I running from 1 to n, subcollection of this IK, k running from 1 to n, such that IKI is equal to AIBI, and then well, first one that we wanted is A1 less than A, and then AK plus 1 is less than BK for all 1 less than or equal to K less than or equal to N minus 1. Yes. And B is less than Bn. Yes, that's it, done. Thus, summation 1 to n, length of Ik which is bigger than or equal to summation 1 to capital N length of IKI, which is equal to summation 1 to N BI minus AI. Let me just rewrite this whole thing. Sorry, it should be from capital N. Capital N, right? Up to capital. Yes. So now let me rewrite this one. Let me start from the last term. I have Bn, and then the remaining, let me write it as minus summation 1 to N minus 1 AK plus 1 minus BK. Whatever we did here in the above calculations, we are going to do the same thing. There we had only one term. Now we are doing it for n terms. And then we will be left with the last one, which is A1, the first term, sorry, which is A1, right? So as usual, middle term, it's a negative quantity and we are subtracting this, therefore it's a positive one. Therefore, this is bigger than Bn minus A1, and the conditions, whatever we have imposed, tells us that this is bigger than B minus A. Therefore, summation over K in N, length of Ik is bigger than or equal to summation K running from 1 to N, length of Ik, which is bigger than B minus A. So, you choose any open cover of intervals covering the interval, given interval capital I, then it is going to be bigger than B minus A. That's what we have done. Right? And we are done. So thus, we are done with this case. Right. Now case 2. Now, I is any bounded interval again, that's usual epsilon trick. Let epsilon greater than 0. Now what you do is you choose two closed and bounded intervals. I1 and I2. Such that I1 is contained in I, which is again contained in I2, and now the other way is going to happen. Length of I2 minus epsilon is less than or equal to length of I, which is again less than or equal to length of I1 plus epsilon. Yeah. So you will have to be very, very careful in choosing this. So I'll simply say how. Yes. Not a difficult one, but it is possible. It requires some patience. So having said this one, now everything is easy. Therefore, by case 1, yes. So length of I1, I'm going to use, I wanted to use, so I'll have to show that length of I minus epsilon is less than or equal to m star of I, which is less than or equal to length of I plus epsilon. That's what I wanted to show. Yes, so length of I minus epsilon. Yes, so length of I minus epsilon, what do we have? If you use the right hand side inequality, this is going to be less than or equal to length of I1. But I1, it's a closed and bounded interval. Therefore, this is same as m star of I1. right? And I1 is contained in I, therefore this is less than or equal to, use the monotonicity. So this is same as m star of I, right? So I1, so this follows from, well, this is from case 1. This is from the monotonicity. Monotonicity of m star I, again by the same thing. I is again contained in I2, so you will have less than or equal to m star of I2 by the same monotonicity. Now I2, it's again a closed and bounded interval. Again use case 1 to conclude that this is same as length of I2. Now length of I2 is less. This is from the left hand side inequality. Yeah, the first one is from the right hand side inequality. Which is less than or equal to length of I plus epsilon. That's it. So thus, what have we shown? M star of I. On the other one hand, I'll have length of I minus epsilon, which is less than or equal to length of I plus epsilon. That's it. So since epsilon greater than 0 is arbitrary, it follows that m star of I is equal to length of I. Right. The last case, I is any unbounded interval. Yes. So how do you show that something is unbounded? What do you mean by something is unbounded? So yes, how do you show that something is unbounded? What do you mean by that? What do you mean by an unbounded interval? What do you mean by an unbounded interval?
Sir, if it is unbounded above, then for every m greater than 0, there exists a point in I mean.
So for each
For each m greater than 0, there exists a point in interval I
right.
such that that point is greater than m.
Right, that's right. Fine.
And similarly, we can define unbounded below.
Right, unbounded below. Right. So now here it is an interval, unbounded interval. Therefore, since I is unbounded, for each n in n, choose a closed and bounded. In fact, there exists. In fact, why choose? There exists a closed and bounded interval in such that in is contained in I and length of in is at least n. Right? This much we should be able to see. And therefore, m star of in is contained in this, which is bigger than or equal to m star of in. Now, in is a closed and bounded interval. Therefore, by case 1, this is going to be length of in. And length of in is at least n. And this is true for all n. That implies that m star of I is infinity. That's it, done. And that's exactly what we wanted. Yeah, we have covered all the cases, right? So here is an important property for the Lebesgue outer measure. I'll put it as a lemma, but still the proof is quite easy.
Sir,
So, yes.
sir, in case second, how the inequality means
Which inequality are you talking about?
sir, I subset of I2. And first
Case 2.
inequality before.
Case 2.
Yes, sir. How?
Which
Yes,
one
sir.
Which one are you
Where
explaining?
how is written?
Length of the I1 contained in I contained in I2 and length of I2 minus epsilon less than I. This one.
Sir, length of I is less than equal to length of I2, and I think length of I2 will come there,
No.
right side.
There is an epsilon which you have missed.
But length function increase with the if I subset of I2 and length of I is less than equal to.
I have subtracted epsilon. They are very close. That's what I wanted to say. The intervals I1 and I2 are very close, and therefore this happens. Fine? Is that clear? I have written
Sir, we
yes.
sir, length of if length of I1 is less than equal to length of I, then we can subtract epsilon
See, there is no doubt about
from left side.
less than or equal to length of I, less than or equal to length of I2, no doubt. I'm not denying that part. But then the second one is something more than that. It is not the same statement as what you said. It is something else. Length of I2, even if I subtract and if I subtract, so I've already chosen an epsilon. So this I1 and I2, they depend on epsilon. That's what I wanted to say. The intervals I1 and I2, they depend on epsilon. Based on the choice of epsilon, this I1 and I2 is being chosen. And I don't want to give what they are. Of course, it's not a difficult one, but I don't want to spend time on that. Just spend time, you should be able to. Is that fine?
Okay, sir.
Yes. Lebesgue outer measure is translation invariant. Right. So what does it mean? That is, for any E subset of R and for any X in R, M star of E plus X is same as M star of E. So let me just write what this is. E plus X, yes, consists of A plus X, so that A belongs to E. Yes, so this is what E plus X means. Maybe I'll put a, so this is the definition. So when there is a 2 dot, that means we are defining something. Yeah, so how does it follow? How does this one follow?
Sir, we can scale the covering collection by X.
That's it, done. Right. So if you have a collection, any open cover by open intervals of E, if you scale them, they are again going to be open intervals and they are going to cover E plus X. Or if you translate them, not scale, sorry, translate. If translate the same cover, if your IK is an interval, then IK plus X is also an interval. First thing. Second, if you have a cover for E, the corresponding translates will cover E plus X. And if you have a cover for E plus X, then translate by minus X. That should be able to cover E. Yes. So proof, I'll simply say exercise. Right.
Sir, can you repeat this?
Sure. Observe that if IK is if I is an interval, then so is I plus X. In fact, if I is an open interval, then so is I plus X. Whether it is, whatever be the property of I interval, so is I plus X. If U alpha, alpha and lambda is an open cover, for E, then this one, U alpha plus X is an open cover for E plus X. That's it, done. So these are the things that you need.
But sir, here we are taking E as an arbitrary set.
Mm-hmm. Even there, it's an arbitrary set for any E subset of R. Well, E is an arbitrary subset of R, of course. Even there, same thing.
Actually, we are shifting the E from
Yes.
by X.
In fact, so U alpha is an open cover of R E. Why then? In fact, if and only if. This you can observe. This is not a difficult one. This is an open cover for E plus X. And these two should tell you that it is translation invariant. Fine, so let me stop here. I will have a break for 10 minutes. And then we'll come back at 10 for the tute. Fine, so be prepared. Have your tute sheet ready and then we'll proceed. Let me stop the recording now. We'll meet again at 10 o'clock.